This is lecture 18. So we are discussing the scheduler code, reschedule of Xenu, which is called in our example from the upper half, say through sleep MS, but it will hold for any blocking system call, or from the lower half, because for two reasons that we're emphasizing: to wake up, which is the counterpart for sleep, or to keep track of the time slice that the current process has currently used up. And if it hits zero, that means that the current process has used up its entire time budget. Then we call the scheduler so that it can then decide whether to have the current process continue or whether to context switch it out for some other process. And so we are inside this function reschedule. We said ignore this part here. Anything with defer, just defer it for later until we get to this stage. It's a minor issue. It's not important and it's not needed to understand how scheduling works. And we have these two pointers to the process table entries of the old guy, meaning the current guy, which may be uh, kicked off the CPU, and then the new guy, which potentially may become the new occupant of the CPU. And we put the address of these two entries uh, here. So this is the current PID, the global for this guy. We store it into this variable. And then we check if the state of the current guy, the old guy, is equals to current. And we know that in Xenu, we are going to, before we call reschedule, from the upper half or the lower half, we are going to set the current process's state to be what it wants to be in the future. So if we are making a sleep system call, then before we call reschedule, we set the state to be PR sleep, because it's making a blocking system call. It is unconditional that we're going to evict that guy and bring some other process in. From the lower half, this guy was running happily, and then there was an interrupt, either from a clock or some packet coming in. We are focusing here on the clock interrupt handler as the main means to understand how the kernel is architected. And in that case, obviously, the current process was running. It wants to keep running, but the kernel may decide to forcefully kick it off the CPU, because during wake up, a process that's been sleeping that has a higher priority now has become ready. And by the invariant that we discussed, we want that process to become the current process. Or the current process has used up its time slice, its quantum, so that has hit zero, and that's monitored, that's maintained by the lower half, in particular the clock handler code, and that checks that it has hit zero. And now it calls the scheduler so that the scheduler can decide, should the current guy continue to run or should it be evicted? And that depends upon who is the highest priority process at the front of this priority queue that we mentioned in Xenu, called the ready list, where all ready processes are maintained in decreasing order of their priority. So the guy at the front of the list is going to be the process of highest priority that's ready. And we are comparing that. And if the current guy, the old guy, has strictly bigger priority than the front element of that list, this is just a macro that just reads its key, which is the priority field, then the current guy, of course, continues to run and it just returns. If this is not true, then it means that the lower half, because this is true for the lower half condition, in that case, the current guy, that is the old guy, is going to be evicted and there will be a new occupant of the CPU. And so we are setting the old guy state to be ready because it wants to keep running, but we are forcefully going to evict it. So therefore, we are going to change its state to ready. That's obviously correct. And then we are calling a kernel function insert to insert this guy that we are now evicting from the CPU. We are now putting it into this priority queue called the ready list. So this is the guy that's being now put into the ready list in its proper place, with the key value being its priority, so that it's placed exactly where it needs to be. And then we are here, which means that we are for sure going to now change the occupant of the CPU. So who becomes the new occupant? The guy at the front of the list. So here for sure we are calling a function dequeue to take out the front guy, who is the highest priority guy, and then we make the global variable here to be this guy's PID. So that's where this is useful. And then we get a pointer to the process table entry of this guy, store it into this pt new variable, which is a local variable of the function resketch. And then, of course, we are going to set its state to be current, because it's now becoming the occupant of the CPU. We give it a new time slice, a quantum, which is given here by a constant. You will get to check all of these things. And then, most importantly, we make a function call to this function called context switch, where we are passing two arguments, one an address to this field in the process table. And this field, if you recall in an earlier lecture, I asked you to just ignore it. We call it in words the saved stack pointer field. This field of the process table entry of a process is only meaningful when we are context switching. That's when it's meaningful. So it has the word stack pointer, and you may think, oh, therefore it is critical when we are pushing and popping something from the stack. Not so. This is only something where we store very important information that's needed when we are context switching, which means that we are kicking a process off the CPU and we are bringing in a different process as the new occupant. And we will see shortly what that is. But keep in mind, we are passing two arguments. That is, we have two arguments here of this function, which pass addresses, pointers of this specific field, of the old guy as the first argument and the new guy as the second argument. And this function context switch is coded in assembly. So this is a case where C function translated by GCC into machine code is now going to call a function that will be coded in assembly, which we are going to now look at. And keep in mind CDECL and the fact that we are now passing to this function coded in assembly two arguments like so. And when all of this is said and done, then this function returns. Returning meaning it returns back to whoever called resketch. And we talked about the different pathways, the top-down pathway number 1, and then the bottom-up two pathways number 2, and 2 prime as I called it, by which this function may be called. So with that recap, now let's jump into all of this stuff here in the slides. I will come back to after we are done with the code. It's just word upon words to explain what we are sure to understand by reading the code. So the code is the critical element. So all that's missing here is this function context switch. So let's directly go to that code and then we'll just overview the rest. There's some nice pictures here, etc. But this is the missing piece. This function context switch. In your lab, you have practiced coding such assembly code, etc. So this is hopefully by now quite familiar, which is the reason why these exercises were done, so that now when you are learning new things, which is changing the occupant of the CPU, that's something that we haven't yet done or discussed. I've mentioned that it's called context switch, but what that entails, that's something that's completely new. But as I mentioned at the beginning of the semester, all of these things are built on the caller-callee convention that we discussed earlier. That's just a tool that you need to understand inside out to now understand something that's new in operating systems, which is we are going to give the CPU from this process to some other process, context switching. And it's this guy's job to carry it out. And this syntax, this format is familiar because it's the same exact thing that you did in lab 2. So this is just a reminder that we are passing two arguments, the addresses of the stack, the saved stack pointer fields, the first guy being the old guy, the one to be evicted, the second argument being the one to be brought in. So what are we doing now here? So just to recap, keep in mind that we have, where are we now in the software that we're trying to understand? So here is somewhere our main memory. And here is the stack of the current process. So this is the stack, this is the runtime stack of the current guy, meaning the old guy. Old means the current guy, the guy who's going to be kicked out. And it will have done this. I mean, it will have done a bunch of function calls. And if it was, for example, main, and main called at some point sleep ms with say half a second, then what it would mean is that this would be say main, this is the stack frame of main. When it calls this guy, this is not implemented in a trapped fashion, and even in the trapped system calls that you implement in lab 2, we are not switching the stack from user stack to kernel stack. That's the only simplification that we are still using here. So we are still keeping with this stack, with this original stack of this process, the old process. And in this example, main was called by someone. We will come back to what that means. And then main called sleep ms. So there's a stack frame for sleep ms. And sleep ms now is going to call context switch. This guy here is coded in C. This guy is coded in assembly. They have to be able to talk to each other. This guy is done in C, which means GCC translates it. So therefore here is again, this interface is where CDECL again comes into play as a building block. So this is in the case where here we have user mode, kernel mode, upper half, lower half, and here is a process, the old guy, that's now making a system call. Of course, we are not trapping, we are in Xeno always in our kernel mode, but that's beside the point. And here the example is of this sleep ms system call, which then calls the scheduler that we are visualizing as sitting between the upper and lower halves, the scheduler called reschedule. And this guy is now going to call this function context switch. Where do we place it? It's probably viewed also as being wedged in between, but because there's not much space here, I'll just throw here this box, which is the context switch function coded in assembly, and this guy is going to call this guy. This is this scenario. The stack will look different, of course, if there was an interrupt that came in. The interrupt of interest is the clock interrupt, which is either going to, in 2, wake up a sleeping process, but we said this exact mechanism applies to when a process is blocking on a message to arrive, same wake up. So you just need to understand it for sleep, and then you understand it for all other blocking system calls with minor variations. So knowing how things work with sleep is very important because it is the de facto uh, reference point through which you can understand all other system calls that are blocking. So this is the counterpart to sleeping here. You are now waking up, and this is recognized by the lower half as we discussed. Or to prime we said, which is the time slice issue. Did the current process use up all of its time budget that was initially given to it, stored in this constant called quantum? We'll check in the next lab what these values are, and these are things that you are then going to adapt so that it's now going to become close to Linux Windows and how Linux Windows performs scheduling. What Azino does is what we said, fixed priority scheduling. So this is for the top-down direction, path 1. Then there is the bottom-up direction, triggered in our case by the clock, 2, which is wake up, or 2 prime. And if it's 2 or 2 prime, then the stack will look different. So here is another drawing of our main memory. So this is the same thing as here, main memory and main memory. But what will it look like for this same process? Suppose, so this is the stack of the guy that's gonna be kicked out, old guy. And suppose it again executes main. Main is suppose just running, and while main is running, a clock interrupt occurs. And we said that when the clock interrupt occurs, then it jumps to through IDT this code called clock dispatch, coded in assembly. So this is inside this file, but this is the label, the name of the function. What you practiced in lab 2, exactly same thing. And in Zeno, this is interrupt number 32. The next available, because from 0 to 31 are reserved for exceptions, faults, as I noted. And this assembly function then calls a C function called the clock handler. And when an interrupt occurs through IDT, you know that what happens here is the hardware assists by pushing, in our case, E flags, the content of the CS. These of course registers, but their content are copied over, pushed onto the stack, and then of course EIP, which is the return address. So these are done atomically by the hardware. That's where the hardware support makes all of this possible quickly. And then the stack pointer, ESP, will actually point to this address, the address where the return address, this is the return address, has been pushed. And for us, return address is very important because it's an important tool in software engineering where we make software do what we want it to do, including it's a favorite tool that's used by hackers to hijack apps to make the apps or the OS do what the hacker wants it to do. So we are going to focus a lot in this course in the context of operating systems and to understand what this is doing. But the return address is very, very important. And in lab 2, you're already practicing some of it because when you have this divide by 0 actually being done, divide by 0 by dividing x by say 0 in your C code, which gets translated to machine code, which actually attempts to divide by 0, which generates interrupt number here 0. And you know that when this happens and you do IRAD, you actually go back to the same instruction, so you would just keep dividing by 0. But now you're going to play a trick. by making IRAD not go to the same instruction that calls divide by 0-fold exception. You want it to jump to the next instruction. That's the practice, that's the exercise done here. So we are going to try a few different values to add to this return address, hopefully hitting the next instruction, and thereby induce the software to then proceed executing the next statement of this C code. So again, this is a case of manipulating these return addresses to make software do what we want it to do. But going back to this setup, keep in mind this picture. You always have to have a clear picture of what's happening to this stack, to this runtime stack, because it's the most critical element in determining what's going on with software which are making function calls, because this is where all the bookkeeping is being done. In this case, with a clock interrupt, with hardware support where eFlags, CS, EIP, their contents have been pushed onto the stack, and now ESP is pointing here. And what happens next? So we are now going to run the code of this guy here. If it has any local variables, it may use it up, but this area will be for the code clock dispatch inside this file clock dispatch s, just like any other assembly code that you have encountered in the lab so far. And who does this guy call? This guy calls this C function. That's why knowledge of what does it mean for a C function to call an assembly function and vice versa is basic to understanding how software works. This is where the payoff comes in, because now you can use that knowledge to apply it to this more sophisticated context of switching the process that's running on a CPU. And this guy calls the clock handler, which is C code. So now from this guy, we are calling the clock handler, which means, let me show this thing in black. There's going to be this stack frame that belongs to the clock handler function. And what's contained here? It follows CDECL because this is C code. So GCC is responsible for translating this into machine code. It's not you who are coding this assembly code from scratch. You let the tool GCC do its job. But that's good because you have a tool to make it work, and hopefully it's coded correctly. But you cannot not know what it does, because you then need to make sure that you are able to talk to this function in the correct way, and that's where CDECL, this convention, comes into play. And then lastly, this clock handler may then decide, because it's time to wake up a process or the time slice has been used up, to call the context, to call the scheduler, reschedule. So this becomes more messy, because you can see that here the nested function calls become deeper. So now this guy will be for, this guy is the stack frame of who is called by clock handler, this guy, which is the scheduler. So this is the reschedule function. This is either number 2 or number 2 prime. In both cases, it's bottom up, clock is triggering. And then this guy calls the assembly function context switch, which means there's one more stack frame. But this stack frame we are needing to manage, and that belongs to context switch. So at a snapshot, this is how the stack will look like at the moment that this context switch function is being called. And of course, this part we need to blow up. The interface between reschedule and context switch, that's where we are now focused on, because we are looking at this code. So this interface, what's here located? That's of course going to be critical for us. But keep in mind, all of this is going on behind the scenes, and when you look at the stack, this is what's going to be there. One more macro picture so that we are all on the same page here. This is again our main memory, and this is the stack of the old guy to be evicted from the CPU. Somewhere else is going to be the stack of the new guy that's going to be brought in. For the old guy to be kicked out, we need to make sure that we save its machine state. In particular, for our CPU, we have a bunch of registers that we need to preserve. EAX, EBX, ECX, you have used some of those in the lab so far. ESP, EBP, there's also ESI and EDI. In Intel terminology, these 8 registers, so there are 8 of them, are called general purpose registers. It's just a terminology. There's nothing general purpose about ESP because it has a specific purpose, but that's not the point. Compared to other registers that we're using, some that I have mentioned, such as CS or CR0, these are certainly of a different caliber. But these are general purpose registers whose main character are that what is contained here influences the ongoing computation by a process. So these are things that a process always tags along. So this is a state of the process that must always be then accompanied by. And so these 8 registers must certainly be remembered so that when the new guy is running, and it may modify one or all of these values, at some point the old guy may need to run more. So we bring this guy in, and this guy then becomes the new guy. But for this guy to continue where it left off, we need to restore all these registers to the values, to their previous values, just before this old guy in the past was kicked out. So we have to save all of these values. We also have to save, as we mentioned, as I noted earlier, this eFlex register, which too is influenced by the execution of instructions of a process. So these 8 registers plus this 1 registers at least are needed. We are not worried about, in this case, the CS register, DS register, SS register, because we said in Xenu, we always run in kernel mode. So we are running in protected mode with P bit of CR0 set on. So we are using all of the hardware support for isolation protection. We just bother not to make use of user mode by having processes start their life in kernel mode and they terminate in kernel mode. So the content of these things don't need to change. And that's the only reason why here we would not have to do anything with these guys, because in Xenu we are not needing to track these guys because we are not switching the hardware state from user mode to kernel mode. If we added that to the trap system calls that you're implementing in Lab 2, then we have more things that we need to keep track of. So keep in mind that we need to, if we are going to modify registers in the function that was called, the callee, we need to make sure that we preserve all the previous content just in case they may be relevant for the previous computation that's going on. Here, previous means the old guy. This is the new guy. So this must all be preserved. And we call in computer science saving the state of a computation. We use a common term, but that's not the only term, checkpointing. So we are checkpointing the old guy, meaning we are saving all the relevant states of this guy who we are now going to evict, so that if this guy is not yet done and it's going to resume running in the future. That's decided by the scheduler, obviously. Then we can put the state of the machine back to the point just before it was kicked off, so that it can continue where it left off and continue correctly. So we are doing a major thing. We are having this process, the old guy, run, fetch, decode, execute all of its code, and suddenly, while it's still not completed, we are now going to yank it off the CPU, and we are going to freeze it. We are going to checkpoint it. And then at a future time, we are going to resume running exactly where we yanked it out. So we need to put the hardware state back into the exact same shape that's relevant for this guy to continue to execute its future instructions as if this yanking had never happened, as if this guy just continually ran from beginning till end. This is, of course, correctness of your software. We must, at a minimum, ensure that even when we yank a process off, then we put it back in on the CPU. So the CPU can, in our case, have only one occupant, one process. And we keep changing that through scheduling and calling context switch as the main operation. We need to make sure that when we do that, at the end of the day, the calculations, the computations that are being done are exactly the same as if this guy had never been yanked out and it was just monopolizing the CPU from beginning till end. And whatever results this calculation or this computation in general that results from such a sequence of instruction execution, it must be the same even if we yanked it out and yanked it back in 100 times. That's correctness. So this is necessary, but it's not sufficient because it's still gotta be fast. All of this has to be done quickly. If it's correct but it's slow, what use is it? It's just not going to be useful in the real world where things have to be fast. So going back to this picture, this checkpointing of saving all of these states, these 8 registers, quote unquote general purpose registers by Intel parlance, and then this eFlex guy, so it's 8 plus 1 at least. Where do we checkpoint it? Where do we save it? We are going to save it in a natural place, which is in the stack of the old guy. That's where we're going to save this state. And then if this guy then becomes current again in the future, then this is where we save the state of these registers. We can then pop them off and then repopulate these registers with these values. That's what we're going to do. So this guy is going to be now kicked out. This is the old guy. The guy that's going to be brought in is the new guy. That guy is going to be brought in. And we're going to make the assumption, this will be soon relaxed, but we're going to now make the assumption that the new guy was previously context switched out. So the new guy, the one that's now going to occupy the CPU, was a process that itself sometime in the past, distant past or recent past, was itself evicted for whatever reason, because it made a sleep system call or there was a clock interrupt, and the clock interrupt then caused that guy to be kicked off. But that means that whatever we are doing here to this guy to safeguard its state so that we can restore it sometime in the future when it becomes current, we had already done that for this guy under this assumption that this guy already ran, and then we context switch this guy out, which means its state, the contents of all these registers, was also, of course, by definition, here remembered. Where? Inside this guy's stack. Now we are going to, when we are bringing this guy in, we are going to, after we save all these registers, repopulate their content with what was saved for this guy sometime in the past. And now this guy now becomes current again, and we have to reset the content of all these registers plus others later on. But for the moment, these guys back to the state, that is back to the values that they had at the time that this guy in the past was contact out. So this guy was in a past, not alive because it's the same life, but it was sleeping, it was hibernating, it was frozen for a while. And at that time, when it became frozen, this guy was the old guy at that time. Now times have changed and this guy is the new guy. But here we are making the assumption that this guy was previously an old guy and now the old guy has become a new guy. And that could again become the old guy, etc., etc. This can happen hundreds of times for long running processes. So, when we are saying conceptually that we are now going to evict the old guy from the CPU, kick it out, and bring in the new guy, then obviously we are now going to have to change the stack. This is the stack frame. This is the stack, not the stack frame of the old guy, the one to be evicted. This is the stack frame of the new guy. After all is said and done, the stack pointer, which was pointing somewhere here, must be updated to point somewhere here. We are doing a major thing. We are actually going to switch stacks. Switch stacks from the old guy stack to the new guy stack. Because this is what's going to be relevant when the new guy runs. All of this stack is needed to do more function calls of the new guy, and also this is where we remembered its previous state. This is where all that information resides. And so, to know all of this and to switch the stack from old guy stack to the new processes stack, to do that, we need to know where the stack is located. But not the beginning of the stack, that we know already. That's part of the process table entry that I already discussed. But what we need to know here is when this guy was frozen in the past, then we need to know where was the top of the stack at the moment that it was frozen. Because it's from here on that we are going to unfreeze it. So the top of the stack, not the entire maximum stack size, but where ESP pointing was pointing when this guy was previously context switched out, that information must be preserved. We must remember that, so that when we are switching the stacks, what does it mean? We are updating ESP, which is now pointing to the top of the stack of the old guy that's now being evicted. It's going to be now updated to point to the new guy's top of the stack. So the address of the top of the stack of the old guy and the new guy is super important. Where do we find it? We find it because we save it inside the process table entry that I called here the saved stack pointer field that I just pointed out earlier. So the arguments that are being passed, so the arguments when we are calling from recache, we are calling context switch. There are two arguments that we are passing as we saw. We are passing addresses, pointers. What are these addresses of? These are the addresses of the process table entry where this top of the stack address of the old guy and the new guy are remembered. For the reason that we need to have that information to switch the stacks and to unfreeze and freeze and freeze a process and then remember after freezing where the top of the stack is, because this guy may have to be in the future unfreezed again when it becomes current. So this is the big picture that you must keep in mind. There are a bunch of things going on that are new. We are switching stacks. We are switching stacks here using purely software technique. As I noted, if we were to implement the trap system calls that you performed in lab 2, which follows the same architecture as the traditional method that's used by Windows and Linux. In that case, if we had added on top of that also this user mode kernel mode uh, switching business, then we would have had to switch the stack not between two processes, old and new. The process doesn't change because it makes a system call. But when a process makes a system call, the PID is the same PID. All that we are doing is switching the hardware state from user mode to kernel mode. And we said that it's critical for isolation protection that we then use a different stack, not the original stack that we're using in user mode, but a different stack in kernel mode to execute all the lower half kernel functions. And this entails, again, a changing of stacks. Like here, we're changing stacks. But one stack here is in a kernel memory, one here is in user memory. And had we wanted to do that, we would have to make use of the hardware support. So in this case, the switching of the stacks that we are here doing purely in software under our full control, this would be done with hardware support. Again, introducing more details about how x86 works, etc., which we are here trying to avoid. So here, using purely software means we are going to switch stacks, and this is a different stack switching from a system call stack switching for a user stack versus a kernel stack, because the name of the process is now changing. If the old guy's PID was 30,000 and the new guy's PID is 40,000, then after the context switch is done, then the process that occupies the CPU now is this guy, not this guy. This guy has been frozen, checkpointed, and it's off, and this guy is going to be the new occupant. So keep in mind all of these pieces, and then focus when we are talking about individual parts so that you can place those parts in this bigger picture. Otherwise, it will very easily get confusing. And this is not the entire story. We need to add a few more things to that so that you can get a good basic picture of what context switching, that is, of what changing the state of the CPU to run a process with PID 30,000 to make it run a process with a different PID 40,000, what that actually technically entails in terms of the software that makes this possible. This is a very, very fundamental and basic operation of operating systems that we need to understand. And if you were to port your own multi-threading package, as I noted earlier, under different process models in user space, and you build your own scheduler in our user space, same thing that we are here doing in kernel mode, in kernel space, following modern kernel design, would just be lifted up into user space. You don't get the full experience because you may not have the hardware support downstairs here that you can make use of to make it go fast. So your software will have some limitations. However, the structure is exactly going to be the same overall as what we are here discussing in the context of implementing it inside the kernel. So with that background here in mind, now let's jump back to the code and wrap up this code here. So we are now executing this code. Keep in mind the stack. Let me maybe throw it here again. I cannot overemphasize that I keep throwing it here, and if you don't throw it, then probably it may still work, but I strongly recommend that at least at the beginning, you keep throwing this stuff to just remind yourself, where am I at in my software? So here is the stack of the old guy. And this is the stack frame of resketch coded in C. And it's calling now this function context switch with 2 arguments, which means that in the stack frame, this guy that's translated by GCC following cdecl would have done what? We know that already. It would have here pushed, let me throw it down here. This guy is called with 2 arguments. So let me call this guy S2, just for simplicity. Let me call this S1. Second argument, first argument. Second argument is the address of the saved stack pointer field of the new guy, and this is for the old guy. So we are passing we are passing right to left, and so GCC following cdecl would have pushed. Let me show it here in green. S2 first, then S1, and then EIP, that is the return address. And you know that well now from all the practice that we've done. So the stack frame here is of course not this, but it's this. That's the content of the stack. At the moment, we are now executing this first instruction of the callee, this context switch function. And in this course, I noted, just for clarity and to make things straightforward, not to try to optimize too much on a few lines of code, which is really not that important in what we are doing here to understand how OSs work. We are going to use EBP, this register, in its sort of traditional mode of using it as a boundary pointer. So the top of the stack here, which is so when we hit this address, the register ESP is pointing here, obviously, because this is the top. And this is the boundary of whoever called resketch. And we said that resketch is called by someone, by some function in the upper half, like for example sleepms, or lower half. Whoever that is, if this guy was using EBP as well by default, then the register EBP, so these are the registers, this would have been used to point to the boundary right here. And above this boundary would be the return address again. The return address that reschedule needs to return to when it's done. It's always the same idea. And there would be arguments, but resketch has no arguments, so there's only a return address up there. It has local variables, so the local variables of this function live up here, but at the top of its stack would have been the return address that this guy jumps back to whoever called it, for example sleepms. And inside the stack frame of resketch, where we are at now, when this guy executes the call instruction and calls context switch, this is going to be translated by GCC because this code is in C code. But ultimately we know that somewhere it will do that. But what does call do? It's going to push the return address, and then it's going to make a jump where? To this instruction in the code segment, in the text segment of the binary. So that's where we are at. And now we want to make EBP point to a new boundary. So EBP is being used to point to this boundary between resketch and its caller. So for us, this guy recache is the caller and context switch is the callee. But like in your lab too, sometimes the caller viewed from this view is the callee, or for example SleepMS. There the SleepMS is the caller and recache is the callee. So always keep in mind which interface are you talking about. Depending upon which one, a function may be a caller or a function, the same function may be a callee. So it has this, in general, this dual roles that it can play in a nested sequence of function calls. And so in this particular setup, it's now calling this guy here with these two arguments, and all of this is done by GCC. So that's where we are benefiting, and we know what format it follows: Cdecl, right to left, return address, and now ESP is pointing right here. But let's say that we are going to use EBP, and EBP should now point to the boundary between this area, which is the stack frame of the callee context switch and the caller. This is what this is actually useful for. So we want this guy to point right here to the boundary. But to say that it points to this boundary means this register will have a different value, namely the address right here, which means it was pointing here, which means that it held the address of this location. If we change that to hold this address, of course, we will lose it. And we don't want to use it because when context switch returns back to recache, we want to make EBP point from here back to here, to the original place. Because now context switch is done and recache continues to run, and EBP should point to where it was pointing earlier. And that's why if we choose to actively use EBP, then we're going to copy this address that this guy is pointing to here. So if this address is address 10 million, this is the boundary between the caller of recache and callee, then we are going to remember 10 million right here, the old EBP value, so that we don't lose it. And then we are going to change EBP to not point here anymore, but we are going to then make it point down here. And that's what this guy does. We are going to push, remember, the content of EBP, which was pointing here, and saving it right here. Push, of course, this is a hardware instruction. It's an x86 instruction. This speeds up by making ESP, of course, not EPS, ESP, -1 decrement. By 1, I mean by 1 word, not just 1 byte. So 4 words, for example, in our width of data, which is going to be 32 bits. So now EBP, the previous EBP has been saved, and ESP automatically, the hardware, sets it to point to here. So now we've saved it, and we now need to make sure that EBP is now going to change its value from 10 million to whatever this address here is, this address. This could be, for example, 9,500,000. Who knows what this address is? This is done through this line. We are copying the content of ESP, which automatically has been updated by the hardware to point to this address, to the beginning of this guy, which holds the saved EBP values. Due to that, we are now going to copy the content of this. We are copying the address contained in ESP, and we are storing it in EBP. So after this instruction now, both EBP and ESP, both of these guys point to right here, to the same place. This is where the return address is, and below the return address, that is at the top of the stack, is now the old EBP. That's what these two things accomplish. So this is getting a bit messy, so let me erase this stuff. So this is what these two lines did. And you have already, a bunch of you, not all of you, but most of you have used these two things to actively make use of EBP, which makes programming easier. It's not needed, but it's easier. It's good for clarity. And then what we do is we remember eflex. That's push FL. So this instruction pushes eflex onto the stack. Push AL is actually 8 instructions. So this is a macro instruction. So this is this guy. Push AL pushes EAX. The sequence should be ECX, ECX, EDX, and then EBX. For us, the sequence is not that important. It's important that we save all 8 of them. It saves ESP, EBP, and ESI and EDI. These are two registers that are used in certain loop operations. So for your assembly code, you should try to avoid using that just in case it's being used for that. But if you're careful, you can use it without too many issues. But these are the 8 registers. That's done in one swoop by this one macro instruction, which is actually 8 push instructions that save these guys. So now what does our stack look like again? Here is the top part of the stack frame of RISC-cache, which contains the return address here, and then the 2 arguments. This is the S2, I think I called it, S1, and then we stored the callers EBP. So this is this guy, RISC-cache EBP, that we just saved, and both EBP and ESP at that junction were pointing here. But then we pushed eflex. So this is the content. EBP continues to point to this boundary, which is useful to know, but ESP, of course, is automatically updated by the hardware now to point to the top of the stack, which contains eflex. And after push AL, what does this guy look like? It pushes 8 register content here. It saves them EAX, ECX, EDX, EDX, EBX, ESP, EBP, ESI, EDI. All of these 8 guys. And then, of course, where does ESP point to? Automatically, after this instruction, the hardware updates ESP to point to the last guy, to this guy, to the beginning of this guy. So that's where we are at after these 4 instructions. And these 9 register values of the CPU have now been saved, have been checkpointed inside the stack area of the old process, the one to be evicted. This is the stack area of the old car. And all that's now needed is, so we are almost done, is since the old guy may in the future become the new guy again. So this is now the old kid because it's being kicked out, but the old kid in the future may become again the new kid. And for that reason, we need to know what is this ESP value. That is, what is this address? If this address is, for example, 9,400,500, so the stack ESP on the CPU contains this address, i.e. it's pointing right here, then we need to remember this address somewhere. So that when this in the future becomes the new guy, we can make ESP point to here and pop off these guys and restore, of course, those register contents. And to make that work, we better know where this address is. So this must be checkpointed as well, and we said that we store it in the process table entry. And where is it? We are passing the address. It's the first argument. I called it S1. Second argument, S2. But where were S1 and S2 saved? Let's focus on S1. S1 was saved right here. This is where this S1 is. But how do we know this address? What is this address? Well, that's where EBP comes in. EBP we've made to now point to the boundary between the caller, reads cache, and the callee, which is context switch. And this guy is pointing to the saved EBP, the old EBP that was remembered here. So, relative to where EBP is always pointing now, where is S1 located? You go 4 bytes up, because this is a 32-bit architecture, so these are all 4-byte one word. 4 bytes up, you hit return address. 4 bytes up, where do you get to? Oh, that's where S1 is. So you have to add 8 bytes to EBP to find the address at which S1 was pushed by the caller, by GCC following cdecl onto the stack. What are we doing here? We are taking the content of EBP, we're adding 8, and that's the reference value that we're using. And so this is now reaching, it's giving us this address, the address where the first argument was pushed. We're pushing these things right to left, as you know from cdecl. And so all that's left is this address, the top of the stack, needs to be remembered. We are choosing to store it inside the old process's process table entry called save stack pointer, whose address is right here. So we copy this address to this EAX register. We can use it because the previous EAX, we safeguarded it, we stored it, because here we are overwriting it. So anything that you overwrite, in general, you need to be crystal clear. Is that being used by someone else before here? If it's possible, you need to make sure that you save it before you overwrite it. We saved it using pushal. That's your responsibility. It's the software's responsibility. So we are saving this address into EAX. And then we are copying the content of ESP, which is pointing to the top of the stack, which is pointing to this guy at this address. That's this guy here. This register contains 9,400,500. We have to now not copy it to EAX, but follow the address contained in EAX. That's one level of indirection. So here, this is one level of indirection. In CS, indirection means follow the pointer. So we follow the address, which takes us to main memory, where the saved stack pointer field of the process table entry of the old process resides. It's in main memory. That's what we're doing here. And we are storing that value there. After this, we are now done saving, checkpointing. Old guy, mission accomplished. So after this instruction, we have now successfully frozen the old guy state so that we can at a future time unfreeze it and make it new, make it the current guy again. So we'll continue from here next time and wrap this up and then switch over to scheduling, which means scheduling algorithms, which is used by modern operating systems like Linux and Windows.